Hey guys, what's up? Eddie Alho here with KissAnalog.com. Alright, so this amplifier's come along. We're really close to finishing up this, promise. I just want to show you what I've done to kind of ump up the power a little bit, okay? Last video I showed how just swapping out that OpAmp, the NE5532 is a great amp for audio. It has a lot of good specs. But the OPA2604 OpAmp that I put in the board, just by dropping it in, it just didn't drop the voltage rails as much. I mean, plus I think it operates closer to the voltage rails. That might be the bigger factor there. And I was able to get 11% more power, right? That was the last video. So, done quite a few videos on this. It's, been making some progress and bringing up the power. Well, originally when I had the problem, when I couldn't get anywhere near 20 watts, and I changed the voltage regulation scheme so that I could bump up the voltage rails on the OpAmp and kind of max out for the NE5532. Then I could get just barely 20 watts before the OpAmp runs out of headroom, which drives the rest of the circuit. So even if I have more voltage out here for headroom, it doesn't really buy me any headroom because the OpAmp doesn't allow it to swing any higher. Okay, so that headroom out here that normally you would have, it really doesn't do me any good in this design. Well, so back in those days, I was looking at OpAmps, and I think somebody led me on to that OPA2604 Burr Brown part. If you don't know Burr Brown, they're acquired by Texas Instruments now, but Burr Brown Analog Devices back in the day, they were like, to me, they're the two analog supreme companies. Just bunch of great engineers at those companies, a lot of great products. Well, the OPA 2604 is not inexpensive either. Now, it came from the little brother, the OPA 604, which is a single OpAmp in an 8-pin package. This guy, the OPA 2604, has two 604s in the package, and it matches the NE5532, okay, pin for pin. So I just dropped it in, got 11% more power. Cool. Okay, two problems. One is I went searching for data sheets before and I found one, but it kind of bothered me a little bit, so I had to go back and do a little more searching, and it kind of bothered me that I didn't find one right out of Texas Instruments. And I didn't work, and I was kind of wanting to get that video out, so I didn't go do all the research. Well, I did more research. I found people talking about the 2604. It sounds like Burr Brown, or acquired by Texas Instruments now, at some point just decided to stop making them. And they didn't really say why, and they didn't really announce that they were going to end of life, as far as I can tell from what I've read online. They just kind of backed out. But it also sounds like, from one guy that left a comment, is that he was able to buy some, but he would have to sign a thing saying that he understands they don't meet spec and that he could buy them. So it sounds like there might have been a lot left in distribution that were people trying to sell, but it wasn't really being supported or marketed by TI anymore. So the only people who are buying them are people like us that are just looking for them, because you can still find them. So I don't even know if they're knockoffs, if they're the real thing or not. I mean, they look like it. They look, as far as I can tell, I don't see any, it's hard for me to tell. From putting them in the board, running them, they seem like they work fine. Okay, now here's what the problem was, is they thought that they're dissipating too much heat. At least that's what I understand. So putting two OpAmps in the same package with that higher voltage, they just said they wouldn't meet the specs with putting, say, plus minus 24 volts in them. So they wanted you to drop the voltage down. Well, I'm going to show you the spec. Let's go ahead and take a look at the spec, and I'll show you why. Alright, so let's start off with the NE5532. Here's the spec, the data sheet. Now, one thing, it's actually better in this regard. 5 nanovolts noise per hertz. And that's at 1 kilohertz. Everything's always at 1 kilohertz, right? But here you can see the specs. You can pull up this data sheet and take a look at it yourself. It's pretty interesting. The slew rate, 9 volts per microsecond. The OPA2604, the 604 is faster, like twice as fast. Both of them are very fast, so that's not really an issue there. All right, and there is the functional block diagram. So it might not be exactly what's in there, but it's functionally accurate, I think. So at least that's what they're trying to suggest. So you can see all the BJT transistors. It's a BJT device. I think that's what you can take from this. The output, you can see it's symmetrical, 15 ohms impedance on each side of the output. All right, so now let's go to the OPA604. Now you can see here application, spectral analysis equipment, active filters, professional audio. So a lot of high-end type applications. Very low distortion. The 10 nanovolts is twice as high, the low noise. JFETs are typically known to have some kind of noise to them, but still these numbers are very low. 25 volts per microsecond, almost 3 times as fast as the other one, but still both very fast. And both of them are, they show 600 ohms as the load. Now there's the block diagram of this circuit. You can see the JFET inputs, the JFET on the second stage, bipolar transistors down here for current sources and things. All right, and as this is a 604, you have 8 pins, so they have a couple out here for trim, so you can kind of trim the input if you really want to get some accuracy, I guess, but it's most cases probably unnecessary. But here's the big thing: plus minus 25 volt power supply, absolute max. And you can see the single op amp in there. Okay. All right, so now let's look at the OPA2604. Again, Burr Brown part, acquired by Texas Instruments. Now, same specs as the 604 is the one we saw before. Same diagram. Okay, but here's the pin numbers. You don't see the 2 pins coming out here to set the bias down here. Now what they're doing is they're showing essentially 2 different op amps, but they're showing for one of them you'd use pins 3, 2, and 1, and the other one you use 5, 6, and 7 for the other one. And then our power rails on 8 and 4. And it's interesting, they show this distortion rejection circuitry, they call it. It's some kind of pending on that circuit, as well as output stage. So they're being a little bit secretive what's in those 2 stages. All right, one thing I want to bring up is this power dissipation. Capo driving 600 ohms up to plus minus 24 volts, so that takes the power to do that. We're going to go look at some power curves. All right, so you see this curve here, 600 ohms. We have the worst case sine wave here on the top, music here in the middle, or no load here at the bottom. And 24 volts is to the far right. And now this is 604, right? So I want you just to note what it's showing here is that you have this 0.3 watts right here in the middle. And let's just say 24 volts for, let's say, music. You're going to be right up here between just under 0.4, let's say, okay? Okay, now this is the curve for the 2604. You see the same curve here for music come up here. Now, instead of just below 0.4, which would be down here, we have 2 op amps in the circuit. This is for both of them running at the same time. So we're essentially double that. We're up here, okay? And that's why I don't think we're going to have that scenario in our circuit. Okay, in this section here, I just wanted to show you this, that you might want to come back and look at this and read it. They talk about sound quality, and they talk about the human ear, odd harmonics, even harmonics, all this stuff. And they're all this stuff related to harmonics and how they think the human ear hears that. And they say FETs are like vacuum tubes. Okay, so then right here, what they're talking about is if you look at the FFT of, say, this circuit here, driving the base of this BJT transistor and taking the output off the collector, you would get this kind of distortion, all these distortion peaks. And with the JFET, you'd typically get this kind of distortion. And I think that's why they're saying that it's supposed to be better for sound. So, I'd like to hear what you guys think. All right, so that's my theory. From the spec, driving into 600 ohms, if you have 24 volts on it, you're going to dissipate some wattage. In our case, one of the op amps in this package is driving a higher resistance. It's part of the servo loop, so it has not 600 ohms, it has kilo ohms in front of it. And the other one, I think, that one's a little bit harder to tell, it's not so obvious, but also I think it's kilo ohms, it's not 600 ohms. So what I think is that both of these guys in this design are driving at least half the load that this thing was spec'd to. And so even though we're operating a higher voltage, we're not driving that kind of 600 ohms impedance. So I think we're going to be fine. Now what I did is I measured that op amp, put a thermocouple right on it, and I'll show you. But I only saw about 25-degree rise. Yeah, it's about 25, 26-degree rise. So I think it's okay. But I'm going to bring the camera over. I'm going to show you how much power. I'm going to show you what it looks like. And I'm going to show you these little heat sink ideas I have, just to be safe, right? I got these little heat sinks you put on chips. I'm going to show you those. And I thought, what the heck? I'll just put one of those on the chips too, just to feel extra safe about the whole thing. But yeah, I think I'm going to be good to go. I'm going to make these changes. Here, let's go look at the schematic real quick, okay? And I'm going to show you what the schematic looks like. Alright, so now we're looking at the schematic, and this is the one in microcap. This part of the schematic you can see right here. This is the output circuitry, of course, and then we go back here to our op amps. One of them is the servo loop. It's taking the output. It's a very low frequency. It's just to make sure there's no DC offset. And that's because of the input. You see no capacitor between the amplifier and the signal. Because if there's any DC, this guy is going to come back here and offset that right here and cancel that out. That's the idea. So this guy right here has a 10K resistor that it's driving. That's a lot bigger than 600 ohms. So this guy right here is not going to be dissipating very much power at all. Okay. So that's a great theme for us because it's almost like we just have a single op amp in the package. Now, this one is connected to our input and it's driving out, and it's coming in to this, and it's basically taking this guy, which is setting up the voltage between these two transistors, and it's just pulling it up and down. And you can see 4.7K, another 4.7K, and we have a 3.3K right here, so it's really driving this 3.3K. And as it drives current into this, it turns this guy on. As it pulls it down, it kind of turns this thing off, so you get more voltage drop. So this guy also has more than 600 ohms. I think in our case, we're not going to have that heat problem that you would if both these guys are driving 600 ohms, okay? So therefore, we're going to try to drive a little bit more power. Okay, so let's come over to our power supply section. And over here is our input, our plus minus supply row. But we have these capacitors and all this circuitry is on the board. These two guys are not on the board, otherwise everything's on the board here. So what we have is, essentially this is a linear regulator, okay? We have an output cap, and this output cap is feeding this voltage rail for this op amp. But you notice if you follow down here, if I highlight that, you see it's connected to this 100 mic cap too, because there's also these two little 100 mic caps sitting right next to the chip. So we've got 100 mic, which these chips don't take very much current, so these guys really are enough. This one over here is pretty big. I'm going to put 100 mic cap here. Okay, then if you follow down here, we have another 470 mic cap. Well, that's gigantic for this base. That's just keeping this filtered right here. This is our reference voltage, okay? So this Zener diode sets up how much voltage we get out here. And this is the Zener diode I'm changing to get higher voltage. Before it used to be only 15 volts. I couldn't get very much power out. I bumped that up so that I could get 22 volts out here, or close to 22, 21 and a half. Now I'm going to bump this up so I get 24 volts. That's an additional voltage on both rails because I also get it down here on the negative rail. So I'm getting more voltage on each rail. So you set up this voltage right here, and then you have 2 diode drops to this point. In this case, we have a Darlington. So any current going into this base, let's say this transistor only has a gain of 10, which has a lot more. But let's just say it had 10. You'd have 10 times more current here. Well, then it goes in here, and this transistor is going to have a gain, let's say only 10. So now you're a gain of 100. So whatever little current you got trickling through here, you're going to be able to get 100 times that out here, which is plenty for this op-amp. So what I'm getting to is this guy here does not have to be supplying any bulk, capacitance. This guy's just hold this thing nice and steady, but we have a 1K capacitor, so that is a huge time constant. 1K and 470 mic, gigantic. So this guy could be maybe 10 microfarads. This guy could be really small. I think it's a 39 microfarad cap that I'm going to put here. And then this guy are the 2 big ones at the front of the board where the power comes in. And they're just cleaning up the power for, see how they're tied to this rail too? So these guys are supplying clean power to these rails and also to this, which there's not very much current here, so they're not supplying it. Mostly what these guys are going to do is supply current to the transistors down here. And then the rest of our power supply will be supporting these capacitors and helping these capacitors stay charged up, essentially. All right, guys, we're back here at the setup. Here's the amplifier on the heatsink. It's not bolted down right now. I had to remove it so I could solder the new parts on. You see silver caps versus yellow caps. And this is our linear regulator with the Zener diodes. This is the thermocouple on the IC chip, just so I can measure the temperature. And and we're going to measure the voltage on the op-amp there. And this guy here, what I want to do is I want to show you the difference in these caps. That's 100 microfarad, and the little ones are 39. So here, let me just put the cap I took off on here. I measured all of them, and much to maybe our surprise, so far the components I think seem real and good. These 4 caps all measured the same value, so I'll just show you one of them here. They were all very, very close to each other. Okay, 466 microfarad, ESR's 0.03. Okay, that's pretty good. Here's one of the caps that I'll be replacing that with. This is 100 microfarad. Okay, he's a 50 volt cap. Let's start him off. Okay, so he's 100 microfarad, 0.02. So yeah, I thought it was going to be a lot better because I didn't think those caps were going to be as good as they are. But they're pretty good caps actually. But still, this one's lower ESR. And we're going to, from the data sheets, we're going to see that these are even better than what they seem. Okay? Now, here's the other one, the little 39 microfarad. Yeah, I'm replacing a 470 with 39. So, okay, now let's push the button on that guy. And yeah, he measures right on at 0.06. So these are very good caps. I mean, it's a small, look how small the package is compared to that. Or here, if we want to compare all 3 of them next to each other, these guys are pretty darn close in size. Okay, now let me show you something. Magic, look what happened. So this here is an engineering kit. These are very nice to get. You can get them from Chemet. You get them on Mauser. And look at the assortment of caps in there. So the ones I'm looking at are these 100 mics right here, 50 volt. Now, I could have used this, the 35 volt. So yeah, I could have used that. They both have the same ESR, so why not? I could just use those and save the 50s. And then I'm using the 39 microfarad for the smaller one, because I really think a smaller capacitor with that 1K resistor is a better option. Very nice kit. But I want to take a break here for a quick minute and just show you the data sheet on those capacitors and show you why they're so good. Alright guys, I want to show you these Chemet capacitors. These things are pretty amazing. Through holes, they have surface mount versions, but you can look into this. They're low impedance, very low impedance, but not just the fact they're low impedance. Here, I'll just kind of show you the values, what it looks like. You can get forum leads if you want, so you know, really nice capacitors. Okay, this is really an important part. The big advantage of this type of capacitor versus a wet type aluminum electrolytic, these solid polymer type, they probably cost a little bit more, but for us, you know, people designing or building things at home, we don't really care probably too much about a few extra pennies or dollars even. But this red curve here is for aluminum electrolytic, standard capacitor. Shows you ESR is higher, but not only is it higher, you see as it gets cold, it just really gets bad. And so essentially that means you have no capacitance because the ESR, the resistance in the capacitor, is so high. Now, and then you can see, like even between -20 and 125, you see how much slope there is. In the blue curve for the conducted polymer, not only is it much lower, but it doesn't change. You know, how much it varies, say from -20 to 125, is not that much. It's not that extreme. And it's more linear. So it's just a much more temperature stable capacitor and lower ESR capacitor. Alright, so I just also wanted to show you the stability of the ESR across frequency. Some people might not be aware that across frequency aluminum electrolytics look a lot different. So let's say switching power supply 100K, great. But look at this 10K, the ESR goes up. Once you go to the lower frequencies, say for 120 hertz or 100 hertz from power line coming in, the ESR is higher. Okay, and then at the very high end they go up too. You get more inductance in the leads. So yeah, you start building some inductance. Now with the conductive polymer electrolytic, it starts off lower, which is awesome, but it doesn't change as much again. Now it does kind of have a similar shape, but it doesn't quite go up as dramatically as the aluminum at low frequency. So, you know, if you need something around 0.1, then you're good all the way across the band, and it just goes out just at the, you know, lower frequencies. So again, for 120 hertz, you know, 100 hertz type filtering at the power supply, still going to be lower. You're not going to lose as much as you did with the aluminum electrolytic. Okay, so more stable across frequency. Now, this is basically showing what happens if you have high ESR and high ripple current. You know, you're going to create too much heat. So the blue shows the better capacitor, the lower ESR solid conductive polymer is able, because it has lower ESR and all that stuff, it can actually handle more ripple current. So you can see the current here on this side. So there we go. Another advantage. And by the way, this is at 100 kilohertz example. That's the way they mark them. And that's the construction. Thought I'd just show you that picture. All right, guys, we're running. We got full signal coming in here. I'm going to show you the voltage here. Put the ground on the ground pin, and I'm going to go to the negative supply rail. And we got minus 24.28 volts. And I can't quite get to the positive one because of that goop. It's actually kind of flopped over the side. Okay, let's go ahead and bring up power. The signal's on full blast, so we're going to see it flat top in the beginning. There we go. And as power comes up, we'll see it. There we go. And just give it a moment for the caps to fully charge, and you see the tops go back to sinusoidal. That should be at max power. Our THD is looking at 0.035 right now. And look at this. We've 15.4, 15.5, 47, 58. I don't know. It bounces around. Over here, frequencies 1K, RMS 1.86 amps about. I'm going to freeze that. Okay, I froze it at 15.53 and 1.87. And you know what? I'm going to unfreeze it. I'm going to go to 29 volts and see if we still get the same output. Yeah, look at that. So, well, I see a little flat top. Yeah, the distortion went up too. So hold on a sec. Maybe 29 is too low. Okay, there's 30. Yeah, it looks like it might have to be closer to 31 to get clean signal. So about 31 volts we need. Alright, so really all it took is Zener diodes working on essentially that, well, it is a Darlington pair that it's driving for that, you know, kind of a discrete linear regulator circuit. And instead of having those big, you know, these big caps on here, what are they, 470 mic caps? They just seem huge in capacitance anyway. Well, they're only rated for 25 volts. On the board, it even calls out for 35 volt caps. So I think originally they had different intentions, you know, and I think that's why in the earlier video that I had to do to bump this up to 20 watts, I had to change the Zener diodes. Well, now I'm changing them again to get that extra voltage. But now that I'm going to have about 25 volts here, or close to what the 25 volt rating of these caps are, I'm going to swap them out with some chemic capacitors. And they're really good capacitors. They have really low ESR. They're solid aluminum capacitors. So I'll show you those too. So let's come over to the bench. I'm going to show you physically what these parts look like. Let's do the test, and the proof's in the pudding, right? And further testing, I'm going to start putting it in the box, getting the box all put together, and we'll run a bunch of power tests with both sides of the amp run at the same time with the real power supply. And I guess that part wasn't settled on before, but we're going to settle on that. And let me know what you guys think. If you guys know any more background information on the 25604. Now, if you like that design, I would design in 604s, because those you can still buy. They still make those. No problem with those. It was just a 2 in the package dissipation problem. Maybe they could have changed the load, or, you know, I don't know. Anyway, yeah, it's too bad they stopped, because if you're not driving 600 ohm loads, then you're probably okay. Or, you know, yeah, anyway. All right, guys. Hey, let me know what you guys think. And looks like we're getting close, huh? So, yeah, I'd like to see your input. And, yeah, so, hey, by the way, I want to thank my Patreons for helping support the channel. That's really awesome. I really appreciate that. And thanks for all you guys watching videos, commenting, and all that stuff. And it's been great. Oh, you become a patron for as little as $1 a month. So, toss that out there. All right, guys. Thanks a lot. I'd like to hear what your comments are on this. It's been a journey, right? And we're going to button this thing up really quick. And we'll see you next time.